today's lesson on inflection and shape. So we're going to be looking at inflections, and typically inflections are used, or we talk about them when referencing two different types. Horizontal inflection points, which we get from the derivative, first derivative, and non-horizontal inflection points, which we have to identify by using the second derivative. So that's what we're going to be looking at today. Before we go on to that, we have to talk about the shape of a curve. Sometimes, obviously, curves will have different shapes. Sometimes they will be concave downwards. In other words, the push or the indentation is coming from the bottom of the function, or concave upwards, where the top is where the pressure is coming from, and that's what's forcing it to curve in a downward motion. So just remember that it's opposite of what you think. Where it's pushing from is actually where it's concave from. Test for shape, you can, by looking at the derivative function, if the derivative function is always decreasing. Now notice here, the slope, in other words, the gradient is 2, then it's 1, then it's 0, then it's -1. Aren't those values always decreasing? It goes from 2 to 1 to 0 to -1 to -2 and so on. So if the derivative is constantly decreasing, it's concave downwards, and that's actually where it comes from, that the derivative or the gradients are decreasing, it going down. Same, or the opposite holds true. Notice these are increasing, so that's -2 to -1 to 0 to 1 to 2 and so on. So that's what makes it goes concave upwards. Its derivative, okay, its velocity is always increasing. All right. So points of inflection, some other things that we need to recall. Points of inflection. We can have horizontal points of inflection, which we already found. Today, by using the second derivative, we talk about the non-horizontal points of inflection, because we've seen them happen already. Here's a stationary point of inflection, or in other words, a horizontal point of inflection. We saw those occur where it would remain negative and negative. It was always decreasing throughout. Okay, that's a stationary inflection or a horizontal inflection point. Sometimes we have non-horizontal inflection points, like this one, or, again, like that one, and they are non-horizontal. And the only way to find those is to do the second derivative. Okay, so we're going to have to do a couple different things. Now here, what you see, the sign diagram of this function is negative, negative. The sign diagram of the second derivative, okay, these are positives, but then they become negative as it goes below. So we'll take a look at that as we continue on. But horizontal or stationary inflection points we find by doing the first derivative. Points of inflection that are non-horizontal we find by using the second derivative. Here's kind of a summary of what we look at, and they do cross over. Horizontal inflection points will appear both in the second derivative and the first derivative. And turning points, local minimums, local maximums, we find by using the first derivative, but there's a crossover. So these are inflections. Some inflections are found in the first derivative. The horizontal inflections are found in the first derivative, and they're still inflections. The non-horizontal inflections are found in the second derivative. Okay, concave down, concave up. All right, and then something else here at the bottom. Horizontal inflections. If the derivative at a certain point is equal to 0, that's a horizontal inflection. If it's not a local minimum or maximum, it's a horizontal inflection. If it doesn't equal 0, but the second derivative does, that means it's a non-horizontal inflection. So let's just take a look at this. I need to find and classify all points of inflection. So to do that, I've got my function. To do that, the first thing I would do is find the first derivative. Okay, so I find the first derivative. Factor it, which is all I've done here is taken out a common 4x squared. then set each part equal to 0, and solve, okay? So from that information, I can find, I should also look at the graph here as well. So let's take a look at the graph. We go to the graph, and here's what our graph looks like. That's the original function. This is the original function. So notice, what do we have? This point is a local minimum. We have here, it's concave up. Here, it's concave. It's changing direction. It's changing its shape. So this is concave down now, and this is concave up. So somewhere in there has to be a point of inflection. Is it going to be a parallel or a horizontal point of inflection? Possibly, but we need to find that point. Okay, and then those are the 2 points we're going to be looking for. So let's just keep going back to our graph, and let's find out. So first thing I'm going to do, looking at my, I want to do a sign diagram. So I'm going to do a sign diagram based on my function. If I notice on my original graph, it's decreasing. So here it's negative. Until it gets to this certain point, then it continues to be negative, decreasing, and then it starts to increase at this other point. So this is the value 3. This is the value 0, which we found by setting our derivative, 0 and 3, by setting our derivative. So as it approached 0, it was decreasing. As it continued past 0, it was still decreasing. And then at that point, at 3, it starts to increase. So we know that this point, because it continues negative, negative, okay, negative and negative, that tells us there's a horizontal inflection point at that point in the graph. Now this is the sign diagram of the derivative. Before we go any further, maybe we should do a sign diagram of just the parent function itself. Sign diagram of the parent function itself. To do that, we would need to have any x-intercepts, and we would also need to have any asymptotes if there are any. But we can do that. We can go back to our graph and just approximate it. Okay. We know that it is positive until it reaches 0. We don't know, maybe even past 0 it's still positive. Looks like it's probably still positive past 0. Yep, it's still positive as we go past 0, so we would need to find this point here where it crosses the x-axis, its x-intercept. And we also need to find the other x-intercept. Okay? And let's just see quickly if I can do that by looking at the table. By looking at the table, I don't see it zeros anywhere on the table, so I would need to find those zeros in the table to find out the x-intercepts. Right now I can't see any on this, just on the table or the graph, but I would need to find those x-intercepts. Let's go back to the page here. So whatever these x-intercepts are, there's only 2 that are needed. I know that it's positive here, and then whatever the x-intercept is, then it's negative, and then it's positive, whatever x-intercept that is. And we would need to find those x-intercepts by setting it equal to 0 or plugging it in, determining what those x-intercepts are. We could do it by calculator as well. All right, so anyway, we found out the sign diagram, we found the derivative. Well, let's just check something. Let's go a little bit further. Let's find the second derivative. So I take my first derivative, and I do the second derivative. First derivative. And now I do the second derivative of that. 4 times 3 is 12x squared minus 24x. Let's factor out the common part, which we did here. Set them both equal to 0. So now I know something else. Notice the 0 appeared here again. So something's taking place at 0. And something's taking place at 2. So what does that tell me? Well, when I go back to the previous function, right, this is my sign diagram. It's positive, then it's negative, and then it's positive again. So it's changing direction. So what does that tell me? it tells me there's a horizontal inflection point at 0, 5. So if I look at my graph, at 0, 5, this point right here is 0, 5. That's a horizontal inflection point. And let's see, what else does this tell me? There's a non-horizontal inflection point at 2, -11. So at 2, -11, down here somewhere, there's a non-horizontal inflection point. So here it's going concave that way, and then it starts to go concave the other way, because notice we see that curve there. It has to start somewhere. It has to be concave up somewhere. So that point here identifies another value that has a concave or a change or shift or a change in the direction. So that's what we take from that as further. So we can find it kind of, the first derivative will give us those stationary points, or the horizontal stationary points, meaning local minimums, local maximum, but also it will give us the horizontal inflection points. Second derivative will give us both the horizontal and the non-horizontal inflection points. So that's what that's telling us. Okay, and our sign diagrams to go with that. Just a summary again, the zeros of the first derivative and the second derivative. If the second derivative equals 0, it corresponds to a stationary point of the first derivative. Okay, at that point, that tells us that it has a horizontal inflection. So the second derivative will change sign at a local minimum or maximum. So it's going to change from positive to negative, from decreasing to increasing. And we know that. We can see that on that graph. At this point of inflection, or this local minimum, doesn't it go from decreasing to increasing? It goes from negative to positive. Okay, so that's the first key there. And then the second part of this, if a local minimum or maximum of the first derivative touches the x-axis, then it corresponds to a stationary point. So it's a corresponding point. Otherwise, it corresponds to a non-stationary point of inflection. In other words, non-horizontal point of inflection. So we've got a couple issues there, but and we'll talk through these some more. But you've got to work with them, practice them, and take a look at each part of them before you can completely understand all of them. And that's really what it comes down to, is first derivative equal to 0, second derivative equal to 0, finding those points. And sometimes, if they appear in both, they're horizontal, and you're going to find extra points of inflection when you find the second derivative, if there are any.